Okay, so previously we had considered a bar in the longitudinal direction. This time we'll consider a beam in a bending. Okay, so we'll have vibration around the y-axis. Okay, previously we had vibration around the x-axis. Okay, now this is very different. Vibration in the y-axis, so we say a beam in bending. And I won't show this, but if you look in the literature, and if you're curious you can do that, you can find the equation of motion of a beam in bending, and it's called the Euler-Bernoulli beam equation. It's not that difficult to construct, right? I'm not going to do that in the course, but this equation involves parameters that we know, except maybe this parameter over here, P of x t. Well, it's the vertical charge per unit of length, okay, at position x at time t. As I've said, the other parameters are known. E is Young's modulus, A is the cross section, rho is the density, GA or JA is the area moment of inertia, and we know that it depends on the geometry of the beam. So again, we are looking for the eigenfrequencies and the mode shapes that are associated to that. And of course, you should work with the Euler-Bernoulli beam equation with the second hand of the equation replaced by 0 over here. So, yeah. And then you should use, well, the method of separation of variables. This is the same method that we've been using for a bar in traction. I've skipped the details, but again, you can write the solution to be f of x times a function g of t. And if you go through the calculations, well, you see that this g of t is this function here, right? So this I've already done, and the question is, what is this function f of x? And if you go through the calculation, well, you will see that this function f of x, well, it obeys this equation here. Okay, so if we define a variable nu over here, which when you take the fourth power is equal to this quantity here, you can write this equation that gives you the solution of f of x by this thing here. So we've replaced this term over here by nu to the fourth, and now you can take the characteristic equation for this equation over here, and that you can write as sigma square minus nu square times sigma square plus nu square, right? This is sigma minus nu times sigma plus nu, okay, times sigma minus g nu times sigma plus g nu. Okay, so of course there are 4 roots, right? This is kind of obvious from the equation, and these are the solution, right? So now we can write the solution for f of x. You could write it as c1 prime e to the g nu x plus c2 prime e to the minus g nu x. Okay, this you can rewrite as c1 cos plus c2 sine. Okay, and then these roots here will give you terms in e to the nu x and e minus nu x, and this can be rewritten using hyperbolic cosines and hyperbolic sines. So this is the solution of my f of x, yeah, and f of x is, well, part of the solution. Okay, you had x, y x of t was f of x times g of t. Well, we had found expression for y of x t, right? And it was f of x times g of t, and we had an expression of f of x. Now there were 4 constants in there, and you also had an expression for g of t, and there were 2 constants that were involved. I'm not going to rewrite these equations. So now I'm going to first consider the case of a simply supported beam. Okay, so it's supported on this point over here and in this point over here, and I suppose that the distance between these 2 points is L, and that my beam is characterized by the following parameters that I've introduced before. Well, for this simply supported beam, since we have 4 constants in my function f of x, well, we need boundary conditions, and we need 4 boundary conditions. Okay, without going into the detail, it's simply that in x equals 0, well, f and its second derivative is 0, and you have something similar here in x equals L. And if you plug that in the previous equation that we had obtained, and this is this equation with sine, cosines, and hyperbolic sine and cosines, well, you can kind of obtain a condition on nu, and this is the condition that you obtain. And again, you will see similar to the case of a bar interaction, that there are of course an infinite number of solutions to this equation. So there are an infinite number of natural frequencies, and they will, it's kind of easy to see what these solutions will be, because if you want to make this 0, okay, well, you need to make sure that this argument here is equal to a multiple of pi with n an integer. Well, we had seen that the boundary conditions for this simply supported beam were producing a condition that this thing here had to be equal to 0. So we had obtained this condition here, and we had defined nu to the 4th to be rho a divided by e ga omega squared. So this was the definitions of our nu. So of course we know that nu square is given by this expression. So we're going to take this expression here, we're going to square on both sides, and we obtain this equation over here, right? And now we're going to replace this thing here by this thing over here. Okay, so we have then n square pi square is equal to this quantity over here, and you had also the L square, okay, and this thing here, and this is actually going to give you the nu n squared, right? So now we can isolate omega n. We obtain this equation, okay, so we are going to put this one in here, okay, so we obtain an L4, and remember that MB is equal to density times volume, okay, so we finally end up with this equation, and that tells you that there is an infinite amount of, or there are an infinite amount of eigen frequencies, and they are parameterized by this index n integer going from 1 to infinity. Okay, let's consider a second case, which is different from the first one, because here the beam is attached on one side, right, and it's free to move on this side, and this is what we call a cantilever or a cantilever beam. Okay, so again we consider vibration in this direction y, so it's for the beam in bending, and without going into the details, well, we have again boundary conditions. Remember that my solution y of xt is written as f of x g of t. We had an expression for f of x, for g of t. Here there were 4 constants, okay? So we need 4 boundary conditions, okay? And goes beyond the scope of the course to see how you can obtain these boundary conditions, okay? If you plug them into your expression of f of x, it was an expression with cosine sines and hyperbolic sines and cosines, you end up with a condition here which again yields an infinite number of roots, okay, and we'll call each root Rn, okay? If you take MATLAB and you take this way of computing roots of equations that I've shown you before, you will see that the first root has this value and the second root has this value over here, okay? And once you have a root, well, you can link it to nu, and nu is itself linked to omega n, okay? So this is what we are going to do next. Well, we had seen that the boundary conditions, okay, had given us an equation here that links nu n times L to the root of a certain equation that is in the preceding slide, and we had seen that the first and second roots of these equations are given by this value, okay? So what is this value of nu? We had defined it to be rho a over e g a omega square. So as I've said before, nu is linked to the natural frequency. From this you obtain this thing here. So from this equation you obtain this equation. So what I've done is squared on both sides, right? And now what you can do is replace this thing here by this equation, right? So we obtain this relation here, and now we can isolate what we need, and this is the natural frequency, okay? So you obtain this thing here. If you bring this one in here, it will give you an L4, and you know that rho times AL, volume times density, is equal to the mass of the bar. So you can rewrite it like that, right? So this cantilever beam has a number of natural frequencies, an infinite number of natural frequencies. Well, the first natural frequency is given by this expression with R1 1.876, and you have something similar for the second natural frequency. This will be important later for our application example of the glider at landing. So next we'll consider a subsection on reduction of complex systems, and these first slides are kind of a summary of what we have seen before. So we first considered the bar in traction, and we've seen earlier that we can reduce it to a 1 degree of freedom system. So this is the bar in traction, and we had seen previously that you could replace it by a spring mass system with a spring value that is given by this expression, and then you had to replace m by an equivalent mass that takes into account the mass of the bar, okay? We've seen previously that if this bar here has a mass that is substantially smaller than m, Well, you should take the equivalent mass like that. You take the mass that is attached and you add 1/3 of the mass of the bar. And we've seen also that there is another limiting situation where the mass of the bar is much larger than m. And then you should work with this equivalent mass. Well, we've seen that for this bar interaction system, if you want to model things very thoroughly, you should use the wave equation, right? And there you have then an infinite number of eigenfrequencies. But sometimes we are interested in only the n first eigenfrequencies. And then you have seen that you could approximate your system by a number of mass spring systems in series. But in order to approximate these first eigenfrequencies, the number of mass spring systems that you have to consider, okay, mass spring systems is higher than n, and it has to be substantially higher than n. Okay, what you will find in the literature is that you should use at least 2n mass spring systems in your approximation. So this is another way to work, okay, and of course it leads to a system that is simpler than the one obtained by the wave equation. Well, as you can see, I've passed quite a few slides, 4 actually, and 2 of these slides concern bar in torsion. The third slide considers the cantilever with end mass, and the fourth slide considers the beam with mass at midspan. These 4 slides are there for your information, so if you're interested you can have a look. And now we'll have a look at motion transformers. You will see that in a lot of mechanical systems you'll find mechanics such as gears, chains and belts, rack pinion system, lead or ball screws. Okay, and the basic function of this mechanism is to transform motion from an input member to an output member, and you will see that they will lead to reflected inertia formula. And in this section and the next one, the idea will be to approximate a complex system into one that is simpler, but that has the same natural frequencies as in reality. These reflected inertia formula will be used in the course Application industrielle de l'électricité of my colleague David Rouchard, and there they will be used for motor selection, and in the field of motion control industry it will be called motor sizing. Well, the first motion transformer that we can consider is the gear system, and you have got a representation over here. So this is the driving gear, so we'll assume that it's rotating in this direction here with a rotational speed omega 1, and of course the driven gear will rotate in the other direction, okay, with a angular speed omega 2, and what we call the gear ratio, and it will be denoted R over here, is the number of rotation of the driving gear, okay, divided by the number of rotations of the driven gear. So you can write also this gear ratio as a function of the rotational speeds, so it's omega 1 divided by omega 2. Okay, so in this example you have that this wheel here has 15 teeth, whereas the other one has only 10, and you can see of course is that this one will be turning faster than the other one. So if we define the gear ratio here like this, okay, we see that it can be computed by the ratio of the number of tools, but it's the number of tools of the driven gear divided by the number of tools of the driving gear. Okay, you see in this case you will have 2/3 here, which is indeed indicating that this wheel will be turning slower than this gear. So we'll often represent such a gear system looking from the side. Okay, so this gear as T1 teeth, this one as T2 teeth. This is the driving gear and this is the driven gear, and we had seen that the gear ratio is indeed the ratio of the rotational speed of the driving gear over that of the driven gear. Okay, and this R is also the ratio of the number of tools, but here you have to consider number of tools of the driven gear divided by that of the driving gear. So now we can have a look at what happens in terms of torques. So this driving gear is applying a certain torque, and you see that we have a radius R1 over here, and that this driving gear is actually applying a force over here. And we know that the relation between force and torque is given by this equation. So it's simply the force times the radius. And you have something similar for the torque that's being produced on the driven gear. So if we look at the ratios now of the torques, and it's again driving over driven, okay, you see that it's the ratios of the radii, the one of the driving gear and the one of the driven gear. Of course, the ratio of the radii is also the ratio of the number of these, okay, and you see that this is indeed 1 over r. Okay, so we have a relation now between the input and output torques, and the relation is 1 over r. Okay, so remember that we had this relation for the rotational speeds. Okay, so this is kind of consistent, right? Because we expect, if there are no losses, that the power at the input is equal to the power at the output. Okay, and the power here would be torque times rotational speed, and here it's torque at the output times rotational speed at the output. Okay, and you see that this is indeed the case with this two relations. Okay, well, of course, when writing something like this, we forget about friction, and we forget about the efficiency of such a gear system, but we'll come back to that later. Well, as mentioned before, we want to kind of simplify this motion transformer, which is simply here a gear system, so that we can kind of simplify this system with only one axis of rotation, and in this case it will be the axis of rotation of the driving gear. Okay, so on the driving gear it's kind of obvious that this moment of inertia will be the same. So we want to know how this moment of inertia will look like when it's reflected to the driving gear. And we know, of course, that in terms of kinetic energy, well, they should have the same influence. So we'll have a look at the kinetic energy of this moment of inertia. It's turning at a rotational speed omega 2, so we know that the kinetic energy is given by this expression. Okay, so when it's brought back, reflected back on the driving gear, it's now turning with a rotational speed omega 1, and the corresponding kinetic energy will be this expression here, and this is the moment of inertia of this gear brought back, reflected back to the driving gear. And this now gives us an expression of this moment of inertia brought back to the driving gear, and it involves a ratio which is, well, the inverse of r squared. Okay, so this r was the gear ratio, and it was written as omega 1 over omega 2, so the rotational speed of the driving gear divided by that of the driven gear. So now we have a way of bringing back of reflecting back a moment of inertia to the driving gear and obtain a system that is equivalent in terms of kinetic energy. Well, you can still use the same idea and bring this inertia G1 to the driven gear, or reflect it back to the driven gear, and then you have an equivalent system, okay, but around the output axis of the driven gear. So everything here is rotating at rotational speed omega 2, okay. Well, it's the same idea in the sense that you use this argument of kinetic energy, okay. So this reflected inertia of at the output reflected to the output is obtained by this formula. So you take the original moment of inertia at the driving gear and you multiply it by the gear ratio squared. Okay, so in the preceding slides we had kind of assumed that everything was working without friction, and of course we know that this is not the case, so you take the gear efficiency into account to correct for that, okay. Efficiency eta is defined as the ratio of the output power over input power. So we know that P2 output power is eta times the input power, okay, and we are going to write that down for our inertia G2, okay, and we're going to bring it back, reflect it back to the driving gear side. So when we're looking at the output power, okay, we know that it's the torque at the output times the rotational speed at the output, and this one here we know from the previous or the first part of the course, well, it's the moment of inertia at the output times the rotational acceleration. Yeah, so we know that this is eta power at the input, but we're now going to look at it as if it's power on the input, but coming from this inertia at the output that is reflected back at the input. So power is torque at the input times rotational speed, okay. This one we can write it down as this thing here, and so this is my inertia at the output reflected back at the inputs times the rotational acceleration at the input. So now everything is ready to kind of isolate this one, okay. So it's the inertia or moment of inertia at the output reflected back at the input. Well, now you will consider these two, or this equation. It's 1 over eta, okay. You have of course J2, and you have omega 2 dot omega 2 divided by omega 1 dot omega 1, and this is here the inverse of the gear ratio squared. So what do we obtain? We obtain what we had obtained previously, but we have to divide here by the gear efficiency. Yeah, if the gear efficiency would be 1 or 100%, then we obtain the same formula, but of course this gear efficiency has to be taken into account, and it has also to be taken into account in this relation. And how do we obtain this one? Well, we have to consider this thing here and this thing here. Okay, so we'll have tau 1 is equal to 1 over epsilon omega 2 over omega 1 tau 2, and this is 1 over r. Okay, so this is how we obtain this equation here. Well, let's look at an example, and it's a motor with a two-stage gearbox plus load. So we've got the load over here. Okay, the first stage with its associated gear ratio and its associated gear efficiency, and the second stage with its gear ratio and associated efficiency, right? And the idea is that you would you would like to see what is the inertia looking on this axis. Okay, so this is the inertia that is actually seen by the motor. So we have to reflect every inertia back to this axis. Okay, so of course the inertia of the motor and this inertia J1 here, well, that's already defined with respect to this axis, so you'll find it just as it is, right? And so we have here a system that is around another axis. Okay, so it's turning at another speed. So this system here, we have to reflect this inertia back to the first axis, or the axis at the input. So you take J2, okay, you have to divide by the gear ratio squared, and you have to divide also by the efficiency to take into account the efficiency of the gear. Okay, it's kind of obvious when the efficiency is low, you have got here a lot of friction, so the inertia seen by the motor will be much harder. Intuitively you will see that it have to produce more torque to well, kind of compensate this torque, friction torque. So this gives us this term over here, and the inertia on this axis over here, well, it has to be brought back first to this axis and then to this axis. Okay, so J load has to be divided by the two gear ratios squared, and you have to divide by the two efficiencies, the efficiency of the first stage and the efficiency of the second stage. And this is the equivalent moment of inertia seen by the motor. Well, these formula that we've seen for the gearbox, you can also use them for a belt pulley system, so I won't go too much into details. Well, the definition of the pulley ratio, it's exactly the same, but the only difference, of course, is that now the ratio R can be obtained not as a function of the number of T's, but as a ratio of the radius at the output over the radius at the input. Okay, so of course, without a surprise, you kind of have the same formula if you want to, for instance, reflect the moment of inertia J2 to the input. Okay, so this is what you see over here. You divide by the pulley ratio squared, and you have to also to divide by the efficiency. Okay, This is if you bring everything back at the driving side, and you have something similar if you bring it back to the driven side. Okay, so another motion transformer is the rack pinion system. So this is called the pinion, right? And this is the rack. Okay, so the idea is to transform a rotation here into translation that you see over here in the variable. It is characterized by the variable x. Okay, the mass of the rack here is m. The pinion has a moment of inertia j, and its mean radius is r. So you kind of see immediately that the link between the translational variable x and the rotational variable theta is as defined over here. So now we can write the kinetic energy of the system, kinetic energy in translation, kinetic energy in rotation, and for instance you can bring back everything to the input shaft. Okay, so we have to use the fact that x is equal to r theta, and of course then x dot is equal to r theta dot. Okay, so if you use that equation here and you plug it in over here, you kind of find an equivalent formula for the kinetic energy, and you can see that this is kind of a equivalent moment of inertia. So we had seen that the equivalent moment of inertia felt on the shaft, well, it's the moment of the inertia of the pinion, and you have to add an additional term here that comes from the translation of the mass m. Okay, what we haven't done so far is take into account the efficiency. Okay, and of course often this rack is connected to some mass, which is the load. So we're considering here the total mass, rack mass, but also mass of the load, and we arrive at a formula of the reflected inertia felt on the shaft. Okay, and the main difference is that we have now divided by the efficiency of this rack pinion system. So the last motion transformer that we'll consider in this course is the ball or lead screwed system. Well, the fact that it's ball or lead, well, it depends on what happens internally in this system. And lead screws or ball screws are widely used to convert rotary motion in linear or translational motion. Okay, since the output of the mechanism is a linear motion, you see that the torque that is applied at the input is transformed into force at the output. This is what is called the nut. Okay, and so we arrive here at two definitions. The pitch, that's the number of screw revolutions for the nut to travel 1 meter. So it's in revolutions per meter, or you can work the other way around. You can work with the lead, and that's expressed in meters per revolution, and that's the distance traveled by the nut in 1 revolution of the screw. If you want to know more about these ball or lead screw systems, well, I advise you to have a look at this source over here. Okay, so we can have a look at this ball screw system. Well, 1 over P here, that's the lead. Okay, and if theta goes from 0 to 2 pi, well, X will have changed position by a quantity that is exactly the lead. Okay, so this is the relation that links X and theta. You can write it like this, and as I said, P here is the pitch. Theta is expressed in radians, okay, so it's the input shaft angle, and X is expressed in meter here, and it's the nut linear displacement. So let's have a look again at the kinetic energy only of this nut plus the load it's connected to, and we'll call this mass M, and it's in linear motion, so the kinetic energy is given by this equation. But you can try to transform it back, because you have, of course, theta dot is equal to 2 pi pitch times x dot. Okay, you isolate x dot here and you write it as a function of theta dot, and if you plug it in, you obtain this equation. Okay, so you can see that this is kind of an equivalent moment of inertia brought back to the input shaft. So again, we have to take into account the efficiency, and we write the total mass as mass of the nut, okay, plus the load that is attached to it, okay, and then we obtain the reflected inertia. This is what we had obtained in the previous slide, but we have divided by the efficiency, and for your information here I have given you the efficiencies for a lead screw and a ball screw. Well, in this last part of this fourth section, we'll talk about the reduction of, well, mechanisms. What the idea is to break them down in a series of discrete inertia, masses or moment of inertias, and of course it's difficult in such a mechanism to see the influence of the various inertia on because they operate at different speeds. So the idea is to write everything back to a single coordinate axis, and most often this choice of coordinate axis is arbitrary, but I think that very often you bring it back to the driving side, right? So this leads you to a single equation for a dynamically equivalent system, okay? And the idea, of course, is that this dynamically equivalent system has the same natural frequencies as in reality. So far we have reflected back moments of inertia, but you can see that you can do that for other elements, so such as inertia, stiffnesses, damping coefficients, and even external forces. Well, the first example that we'll consider is the lever-linked mass spring system. This system has 1 degree of freedom, although, well, there are 2 masses, but clearly the 2 position variables x1 and x2 are linked through the lever, in the sense that the ratio x2 over x1 is b over a, which is the lever ratio. One way to approach things would be to write down Newton's equation for the 2 masses, apply the constraints, and then eliminate the linking forces. That would be rather difficult. What we'll do is use energy considerations, right? And we'll reduce the system to one equivalent system with one position variable that will be x1 here. Okay, so we'll bring everything back as if there is only one system which has the position variable x1. Okay, so we'll write the kinetic energy as a function first of our 2 variables x1 and x2. That's kind of easy. And then we notice, of course, that x2 and x1 are related. Okay, so x2 over x1 is b over a is equal to r. Okay, so we can rewrite our kinetic energy like this, and we'll define this to be an equivalent mass. Okay, so the 2 linked masses have kinetic energy as equivalent to a single mass, which is this one, and it's computed as follow, and it's moving in the direction x equals to x1. Well, we have looked at kinetic energy, but we can also look at potential energy, and the idea will be, of course, to have an equivalent spring stiffness, and the potential energy results from the deformation of the two springs, and they are linked to the variables x1 and x2, and it's kind of easy to compute this potential energy. And again, we know that x2 is linked to x1 through this equation. We plug that over here and we arrive at this equation here. So we can kind of see that we can use an equivalent stiffness. So we can say that the two springs store the same potential energy as an equivalent single spring with stiffness, which is computed by this formula over here. Okay, we have considered kinetic energy, potential energy, and now we're going to consider the dissipated energy. Okay, and this energy over a certain dissipated over a certain amount of time, well, it's the power, okay, times this time interval, and the power, it's the force, which is minus c1 x1 dot for this term here, times speed. Okay, so this gives us this term over here, and we have something similar for the second system. Since we have that x2 is equal to rx1, obviously we also have x2 dot is equal to rx1 dot. We plug that in here and we arrive at this equation here, and we can write an equivalent damping coefficient. So the two dampers dissipate the same energy as an equivalent single damper with damping coefficient that is given by this expression. Well, we're almost there. So we have two forces acting on the system. We kind of have to see this as an equivalent force acting on this equivalent system. So we have to do this by considering the work that is done by the external forces, and a work, it's force times displacement, right? We know that x2 is equal to rx1, so a variation, a small variation dx2 is equal to r dx1. You plug that over here and you obtain this thing here. So the work of the two external forces is equivalent to the work of a single equivalent external force that is defined like that, and that is acting along x equals x1. So we have defined an equivalent mass, an equivalent damping coefficient, an equivalent stiffness, and an equivalent force. Okay, and the variable that we were considering was x equals to x1. So this system, okay, this lever linked mass spring system can be modeled by an oscillator with a 1 degree of freedom that is described by this equation here. Okay, and if you want to look in the more details by looking at the values of the equivalent mass, damping, stiffness, and force, well, you obtain this equation. Okay, so this looks like this system. Okay, so we have kind of reduced this complex system and we have transformed this to this, well, a lot simpler equivalent system. So here we consider two rotors with torsional stiffness and torsional damping linked through a perfect gear system, and again clearly this is a 1 degree of freedom system, as the angles theta 1 and theta 2 are linked through the gear ratio. And since here there is a torque being applied, we'll be considering this one as the driving gear, so the ratio theta 2 over theta 1, okay, and since we've taken the both angles in the same direction, and we know that with the gearbox, well, of course the two gears are going to rotate in opposite directions. Well, theta 2 over theta 1 is going to be minus r, where r is the gear ratio, and it's defined here as the ratio of the number of tooths, in the first gear divided by that of the second gear wheel. Okay, and we'll use again energy considerations to reduce the system to an equivalent system with angular position, with one angular position, which will be this one over here. Okay, so the kinetic energy of the total system, well, you can write it first as a function of the two variables, theta 1 and theta 2, and you obtain this expression here. You know that theta 2 and theta 1 are linked, and we had theta 2 over theta 1 is equal to minus r. Okay, you plug this relation in here and you obtain this relation, and we kind of have now an equivalent moment of inertia. It's bringing this moment of inertia on the driving side to the driven side. So this is what we had obtained earlier. Okay, so the two rotors have same kinetic energy as a single equivalent rotor with inertia given by this expression and rotating around theta equals theta 1. So we have to look now at the equivalent damping coefficient, and we do that by looking at the dissipated energy. This is given by this expression here, and what you see here is the damping torque times the rotational speed. We have that theta 2 is equal to minus r theta 1, and if you take derivatives and square on both sides, you have of course that theta 2 dot squared is equal to r squared theta 1 dot squared. Okay, so this is how you obtain this equation, and this is kind of a damping coefficient brought back to the axis of rotation over here. So it's an equivalent damping coefficient. The damping on the second rotor is reflected back as an equivalent damping on the first rotor, written as this expression. So you can look at the work of the external forces, and in this case it's of the external torques. Work, it's torque times displacement. Here it's angular displacement, and this theta 2 is equal to minus r theta 1. So of course you have d theta 2 minus r d theta 1, and you plug that in and you obtain this thing here. So we have an equivalent torque here. The torque around the second axis of rotation is reflected back as an equivalent torque around the first axis of rotation, and it's given by this expression here. Okay, so we've kind of found equivalent parameters, okay, for the moment of inertia, for the damping coefficient, for the stiffness, and for the torque, and this allows us to write an equivalent model, which is an oscillator with 1 degree of freedom, and you have the expressions here for the different parameters, right, and for the equivalent torque. Well, in terms of stiffness, of course, since it was already around the first axis of rotation, the equivalent stiffness is of course K1. Okay, this means that this complex system can be rewritten as an equivalent system with equivalent moment of inertia, damping coefficient. Okay, so the torque, the equivalent torque, is defined as positive in this direction, but indeed if it's positive over here, we should expect it on the other side. This is indeed what we see, because this one here is equal to minus r, and the torque that was initially applied, so indeed it's going to be in this direction here. So this is how you can obtain a model for a gear linked rotor system.